bonding in a
At the end
crystal
of this
lattice.
video, I want you to be able to compare and contrast a chemical formula for a molecular compound with one for an ionic compound, discuss the arrangements of ions in crystals, and define lattice energy and explain its significance. Chapter 6, Section 3, Ionic bonding and ionic compounds. Most of the rocks and minerals that make up the Earth's crust consist of positive and negative ions held together by ionic bonding. A familiar example of an ionically bonded compound is sodium chloride, or common table salt, which is found in nature as rock salt. A sodium atom, Na+, has a charge of 1+. A chloride ion, Cl-, has a charge of 1-. In sodium chloride, these ions combine in a 1-to-1 ratio, Na+ and Cl-, so that each positive charge is balanced by a negative charge. Because chemists are aware of this balance of charge, the chemical formula for sodium chloride is often written simply as NaCl. An ionic compound is composed of positive and negative ions that are combined so that the numbers of positive and negative charges are equal. Most ionic compounds exist as crystalline solids, as is shown here on figure 6-12 on page 176 of your text, or on the screen now. A crystal of any ionic compound is a three-dimensional network of positive and negative ions mutually attracted to one another. As a result, in contrast to molecular compounds, an ionic compound is not composed of independent neutral atoms that can be isolated and examined. The chemical formula for an ionic compound merely represents the simplest ratio of the compound's combined ions that gives electrical neutrality. The chemical formula of an ionic compound shows the ratios of the ions present in a sample of any size. A formula unit is the simplest collection of atoms from which an ionic compound's formula can be established. For example, one formula unit of sodium chloride, NaCl, is 1 sodium cation plus 1 chloride anion. The ratio of ions in a formula unit depends on the charges of the ions combined. For example, to achieve electrical neutrality in the ionic compound calcium fluoride, 2 fluoride anions, F-, each with a charge of 1-, must balance the 2+ charge of each calcium cation, Ca2+. Therefore, the formula for calcium fluoride is CaF2. Formation of ionic compounds. Electron dot notation can be used to demonstrate the changes that take place in ionic bonding. Ionic compounds do not ordinarily form by the combination of isolated ions, but consider for a moment a sodium atom and a chlorine atom approaching each other. The two atoms are neutral and have 1 and 7 valence electrons, respectively. We have already seen that atoms of sodium and the other alkali metals readily lose 1 electron to form cations, and we have seen that the atoms of chlorine and the other halogens readily gain 1 electron to form anions. The combination of sodium and chlorine atoms to produce one formula unit of sodium chloride can thus be represented. The transfer of an electron from the sodium atom to the chlorine atom transforms each atom into an ion with the noble gas configuration. In the combination of calcium and fluorine, 2 fluorine atoms are needed to accept the 2 valence electrons given up by each calcium atom. Recall that nature favors arrangements in which potential energy is minimized. In an ionic crystal, ions minimize their potential energy by combining in an orderly arrangement known as a crystal lattice, as is seen on figure 6-13 on page 177, or on the screen now. The attractive forces at work in the ionic crystal include those between oppositely charged ions and those between the nuclei and electrons of adjacent ions. The repulsive forces include those between like-charged ions and those between electrons of adjacent ions. The distances between ions and their arrangement in the crystal represent a balance among all these forces. Sodium chloride's crystal structure is shown in figure 6-14 on page 177 of your text or on the screen now. In figure 6-15 on page 178 of your text or on the screen now, there is shown the crystal structure of sodium chloride in greater detail. Within the arrangement of each sodium cation, they are surrounded by 6 chloride anions. At the same time, each chloride anion is surrounded by 6 sodium cations. Attraction between the adjacent oppositely charged ions is much stronger than repulsion by other ions of the same charge, which are further away.
Bonding in a crystal lattice is controlled by the size of the ions involved and the stability of the final structure with respect to positive and negative charge. The attraction among ions occurs in all directions. In sodium chloride, there is one sodium ion for every chloride ion. Chloride ions attract as many sodium ions as possible. Similarly, sodium ions attract as many chloride ions as possible. In this way, the charge on each ion is balanced as evenly as possible by the surrounding charges on its neighbors. The ions pack together, producing a regular, infinitely repeatable structure called a crystal lattice.
So, the three-dimensional arrangements of ions and the strengths of attraction between them vary with the sizes and charges of the ions and the numbers of ions of different charges. For example, in calcium fluoride, there are 2 anions for each cation. Each calcium cation is surrounded by 8 fluoride anions. At the same time, each fluoride ion is surrounded by 4 calcium cations, as is shown in figure 6-16 on page 178 of your text or on the screen now. To compare bond strengths in ionic compounds, chemists compare the amounts of energy released when separated ions in a gas come together to form a crystalline solid. Lattice energy is the energy released when 1 mole of an ionic crystalline compound is formed from gaseous ions.
For these sodium and chlorine ions, a lattice structure is more stable than a gaseous cloud. Energy is released as they come together to form a crystal lattice structure. 787.5 kilojoules of energy are released when the sodium cations combine with the chlorine anions to form solid crystalline sodium chloride. This energy is the lattice energy.
Lattice energy values for a few common ionic compounds are shown in table 6-3 on page 179 of your text or on the screen now. The negative energy values indicate that energy is released when the crystals are formed. At this point, I hope that you can compare the chemical formula for a molecular compound with one for an ionic compound, discuss the arrangements of ions in crystals, and then define lattice energy and explain its significance.